Abdurrahman Abdullah Al Khzaimi. She was part of the inaugural session. So I'll just briefly read the profile. I've already introduced her. Dr. Huda Al Khzaimi is currently the Director of Center of Cybersecurity in New York University, Abu Dhabi, and a Research Assistant Professor in New York University. She served in different posts for research and development in the technology development sector for the past years. She also played a specific role in developing cybersecurity and cryptology research and development ecosystems. She headed the Department of Research and Development for Cybersecurity and Cryptology in different national initiatives in the United Arab Emirates, along with her associations to different security initiatives, nationally and internationally. She consults for special projects with national and international technology development initiatives. Huda is the president of Emirates Digital Association for Women, a non-for-profit organization endorsed by the Ministry of Social Affairs in the UAE that supports national and international initiatives that aims to empower economic and educational development for diverse communities with a specific focus on women and children. This includes, yet not limited to, establishing and creating ecosystems that support sustainable business development in the UAE and the international scene, which supports indigenous growth of local economies. She is as well the strategic director for Women in Artificial Intelligence Research International Community that aims to improve the scientific and professional positioning of women's contributions within the field, especially in the MENA region. She is the lead of Women in Engineering chapter in Abu Dhabi and the UAE lead for INWES MENA, which is the global network for organizations of women in science, technology, engineering, and mathematics. She is currently focusing on building sustainable economic ecosystems and investments for valuable technological and industrial impacts. Over to you, madam.
Can you enable screen sharing so I'll be able to share my, yes, that's perfect. Thank you so much. Okay. So today we're going to talk about the journey of improving the design of hardware security for symmetric ciphers and symmetric analysis in order to fit into the schematics of emerging environments. And when I say emerging environments, I mean environments that would be dictated in the new emerging technology concepts as what we're talking about today in the metaverse, for example, or in the restricted hardware devices, the wearables. What kind of security parameters are we going to place on these devices? And is the type of security we're developing today enough for that? So my research team and my research group has wide aspects of analysis. A few of my research team members work on the design and the cryptanalysis of primitives of a cryptography, like hash functions, random number generations, and ciphers. And the rest, they work on systematic analysis of placing these primitives in a systematic protocols or models, or either in restricted environments. We have as well expanded to machine learning based models and attacks, and at the same time, multiple arenas of understanding what is the impact of machine learning techniques on electric vehicles and whatnot. So the objective for us here is trying to understand, and I'm sure most of you do have the exposure to this knowledge. The objective of the primary focus of the field of cryptography is to design primitives, either in hardware or in software, with the focus of building lightweight, trustworthy, and efficient cryptographic hardware models. And the cryptanalysis, when it comes to the cryptanalysis perspective of it in hardware and software, the objective is to be able to apply classical techniques like linear and differential cryptanalysis or side channel attacks that has hardware aspects of the analysis, hybrid techniques, and at the same time be able to produce specific security margins. So what we are trying to do is keep up with the introduced limitation of hardware, as I explained when we are talking about emerging technologies and software environments, while maintaining the security parameters or security margins introduced. And at the same time, introduce attack models that will guarantee attack results by more than half of the probability. This is why what we're doing for machine learning attacks on hardware and software, or if it's not a probabilistic model, have a guarantee that the attack would actually work. So we have different categories of crypto systems when we are talking in the wider term. So I'm not sure how many of you are exposed to what we call symmetric and asymmetric systems versus others. So in the symmetric system, you will have the fast encryption models, you will have additional complexity because of the provided key exchange. And while in the public asymmetric crypto systems, you will use, for example, it is normally known as a slow encryption process and key exchanges embodied into different models like what you're having here today in this PKI conference. I'm sure you will be exposed to multiple PKI structures, and you have the mixed models, which are normally provide hybrid encryptions based on this composition of these two models, or also, or either making sure that you are providing dual characteristics, right? For example, the hybrid encryptions that would provide for authentication and encryption at the same time. And it can be, of course, slower a little bit than the norm that we have seen in the past for symmetric encryption. Where can you find these models? I mean, where can you find encryptions on these levels? You can find them on the TLS, SSL protocols, the HTTPS protocols available on your web browsers. And as well, you can find them in contactless, smart cards, and RFID tags. You can find them as well within the satellite communications, within different systems, IoT environments, and multiple encryption systems, mobile systems, as we have just described in the past. So, I mean, why do we need them? I mean, the world is moving toward energy harvesting devices and wearable connected mobility that supports mobility devices. Internet of Things, most of you have heard of them, in smart cities. And now we're talking about digital twinning. We're talking about the metaverse. All of these environments, also the blockchains, the crypto systems, the crypto payment protocols, all of these systems are highly dependent and relying on the crypto that we're building. So for example, as you've seen in the slides here, we have few examples of the different ciphers that are available on cell phones, satellite phones, or cordless phones, and DVDs, for example, and smart cards and secure tokens. But are they enough? You could see that the security margins that are normally defined by the size of the key, the size of the initial IV that is being pushed, and the attack time complexity is on the low side. So if you can see that the key, normally the attack time complexity is governed by the size of the input of the key, because your key is your secret material and we're trying to attack that secret material. So if you see here, the key size, for example, is 64 bits, then the successful attack here is happening for a subset of that, which is 2 to the power 24, which makes it, we'll see in a bit why, a doable attack in polynomial time. And we have to be careful of attacks in polynomial time, because it means these are attacks that are exponential and that are feasible within a specific time structure. So the generic model and the design that we are aiming to look at when I will introduce our attack techniques is something of what you're seeing on the slides. You would have the message, the cipher, the key, the encryption and decryption schemes. that they have to be a bijective function in order to be having a backward compatibility of producing the message. And this is why we need the bijective mapping. When it comes to the structure of those different cryptographic schemes, for block ciphers, for example, we have a family, a box of families that exist for the design of these primitives like SPN, Feistel networks, general Feistel networks, addition, rotation, XOR, nonlinear, feedback shift registers, and hybrid models, and many other possibilities as well. And the reason for this kind of diversity of designs is being able to fit designs into different hardware environment if possible, maintaining security margins, and being able to control specific security margins in order to provide a level of security. For example, this is an SPN structure, substitution permutation network, where you could see the substitution layer represented by the S boxes here. That's the nonlinear layer. And then the permutation layer represented by a mixing model. Normally, it could be defined by MDS matrices, which is maximum distance separable code-based matrices that are aiming to introduce a level of mixing. And then the nonlinear layer aims to destroy relations between input and output, or the mixing layer is aiming to make sure that there is a huge balance between these destruction between input and output, and it would ultimately give you a sense of security in a way that would make a change in one bit reflected in a change of all output bits after a specific number of rounds application. And this is what we call the avalanche effect on the cipher. So for the Feistel structure, again, you would have the input divided into different block sizes. And then you would have what we call the left and the right part of the Feistel structure. So it's a very symmetric operation. And then you would apply, for example, you have here a rotation by 5, addition or multiplication over Galois fields. And this would allow you to provide a level of linearity. The general advantage of a Feistel structure is that you can use the same structure for the decryption without changing massively the design. You're just reversing a few of the operation. You have also the Lemacy structure, the ARX structure. We'll talk about them later on. ARX is very famous in the recent era because it has been claimed that it's very suitable for hardware designs, but as well it has its own limitation when it comes to meeting specific security margins. But is our cryptography enough? Is these designs that we are presenting enough? We've seen in the past that we have issues with providing for security for limited, I would say, implementation devices, like, for example, pacemakers that are placed to control the heart activities would have a very limited bandwidth for extra computation. So when you, in 2007, I remember there are a attack series that has been arising because the medical devices, the medical implant represented by the pacemakers, had an encrypted series of messages, which provided a level of vulnerability to these devices that reflected on the subject matter, on the humans that would endanger their lives. So what we're trying to do here is make sure that our crypto would have the lowest limitations when it comes, or requirements when it comes to the hardware, so it can fit into these physical system components or biological systems without actually introducing much hassle or much limitation. Okay, so we're talking about deep brain neurosimulators, cochlear implants, or cardiac activity controls, insulin pumps, for example, and whatnot. We had recently worked with Mr. Pandian, who is also part of the people who arranged for this invited talk, to work on some medical devices security as well. And I think I would like to encourage the wider audience as well to work on that level of application, providing security for medical devices. Again, when we're talking about the boundaries that we have for the current existing cryptographic primitives, we could see that, for example, AES, SHA-256 and SHA-3 RSA, and then you have the elliptic curve systems, DSA, elliptic curve Diffie-Hellman, digital signature algorithms, for example. They both have specific purpose, but at the same time, with the introduction or the impact of introduction quantum computing on these cryptographic algorithms, we've seen that their security level is not anymore what we have perceived in the past, given regular computing environments. And of course, at a point of time, our definition of regular computing would change. Today, we define regular computing by the current computing environments that we have that would never breach the 2 to 128 kind of operations boundary. But tomorrow, with the quantum computing that has been estimated on a simulation level by IBM leadership to be provided in 2023, it would be larger than the key sizes. Like, for example, for AS256, their security is larger than the key sizes needed, which is good. SHA-3 is larger than the output needed, which is good as well, I think. But for RSA and elliptic and public key cryptography, we're facing an issue because certain boundaries are not going to be secure anymore. This is, of course, pushing us to steer away from standard cipher design or standard security design margins, which are encouraging you to stay within 128-bit limits, to something that would provide a high level of security. So how can we really balance that? Because for providing a secure margins, we need to go with higher number of bits, but for providing for restricted environments that the world is going for, the IoTs, all of these devices that are going on a lower and lower perspective, we need to actually provide lower number of bits for restricted environments, lower chip sizes, lower energy and power consumptions, gate equivalence, latency, clock and frequency and throughput. So we need to find a bit of a balance in between this elements, these hardware elements, and also in between the software implementation that we are providing in terms of the code we're optimizing, smaller RAM sizes, and pushing the gate equivalence to the lowest that we can. So hopefully, I mean, we started with something that's lower than 2000 gate equivalents. Right now, we're talking about ciphers that exist in lower actually than 138 gate equivalents, which is a massive change. When it comes to lightweight cipher proposals, for example, where few of them has been standardized in the ISO IEC 29192 and 2 standards, one of them is Present and Cliffia. We started seeing much more progress on this. When it comes to authenticated ciphers, New Hope and others, solution has been provided. But that's not it. We're still seeing more solutions on post-quantum crypto, and we keep on seeing more of these solutions. You don't have them here in the slides, but for example, our perspective of lightweight will drastically change because this is the old perspective of what we can call lightweight. But now with the introduction of the new hardware environments and computing environments, things would definitely be providing a tougher trade-off, I would say, to be engineered. Because the current trade-off that we have is how can you lower the parameters of the design in terms of hardware and software, and at the same time maintain a high security margin and not get into the risk factor of getting easier crypto analysis models being built or better assurance level being developed when it comes to the attacks that we need to build. So from an attacker perspective, what do you need when you attack symmetric crypto systems in general? And this applies as well for asymmetric crypto systems. What you're trying to do is have a different attack agendas, but ultimately a total break. It means you are deducing every kind of secret material from the system is what you're aiming for. And a global deduction, it means you analyze the global model and you have a global distinguisher of the model and you can break into the system eventually. A local deduction means that you can only analyze few number of rounds and you can deduce the input output of a few number of rounds. A distinguisher attack, it means that you cannot actually get to attack the system, but you can distinguish the nonlinear layers. You can build a characteristic and a distinguisher, either a linear or differential characteristics and distinguishers, and use the propagation of this linear characteristic and or differential characteristic or whatever type of characteristic that you're building to build a probabilistic model. And out of the learnings that will come from this probabilistic model, you can deduce eventually the key with a specific computational complexity. This computational complexity could be something theoretical that's not achievable. In that sense, we will say that the attack is not possible, or it could be something that is actually achievable in polynomial time, which means that we could have it done in practical time. And then the system will be distinguishable and the system will be attackable. So attack models that we have when it comes to probabilistic model is linear cryptanalysis, differential cryptanalysis, and algebraic cryptanalysis. Of course, we're not focusing only on those. We have also side channel attacks, and I'm sure you've heard about it in the room. We work on time analysis, sample power analysis, differential power analysis, fault injections, and others, and hybrid techniques amidst all. So the key length here dictates, this is old school way of trying to analyze the security margins of the system, beside making sure that you have a strong nonlinear layer, strong linear layer diffusion, and having specific boundaries around this layer. Cryptographers or cryptanalysts normally go with the attack input-output sizes, where they would say generically, if the key length of, which is the key is very important since it's a secret material, if the key length is 40 bits or to 256, for example, most of the designers aim to provide multitudes of design options between 40 to 256 to suit different hardware environments. Then the search time will be 2 to 40 or 2 to 56. And in a traditional computation environment, 2 to 40 was an easy model to break. This is why earlier on when we spoke, I've hinted that 2 to 24 is an easier model to break, so we have to be careful. 2 to 64 is practical to break, while 2 to 80 is not very feasible, and 2 to 128 is very strong, and 2 to 256 is exceptionally strong. So this is the classical attack model. What we're trying to do with our attack models is reduce these search times to something very practical and get as close as possible to the practical attack margins. So one of the attack models that we have presented in my group in Africa Crypt, it was around side channels for Spark, and our merit was to analyze addition, rotation, XOR environment or attack design structure, and Sparks was one of these designs, which was, it's a cipher that has 64 to 128. That's the model that we analyzed, but it has many other input-output possibilities. We try to analyze the smallest version using combined DPA, differential power analysis techniques. Combined because we used first and second order differential power analysis and simulated what we call key extraction. So our contribution were like make sure that we explore the correlation power analysis of sparks and propose a secure implementation of sparks against power analysis using what we call threshold implementation. Why did we choose sparks again? Because we are expected in 2025, here, we're saying 30 billion devices in 2020. But with COVID, the last forecast that we had, it's like 50 billion, over 50 billion devices in 2025 are supposed to be available around the world. So how can we make sure that these devices, which are going to be running on a very limited hardware environment, are actually secure? We need to make sure that our designs that are pushing the limits of hardware, that are providing a very restrained and constricted environment, are actually secure for them to be analyzed. So there was, of course, several announcements on lightweight cryptography competition when it was being run by NEST that gave an importance to lightweight ciphers. We had designs that sparked from that competition. We had skinny, sparks, present, prints. Although present was an earlier addition, an earlier invention, prints was one of them. I think present and prints, both of them has been standardized. These are few lightweight ciphers from the 56 submissions that were considered. We chose Sparks because there was no formal security. There was a formal security proof to it, but there was no practical, actually, security analysis or attack towards it. So what we've done is we chose the lowest version from the 3 variants in the family. We provided with the general structure of the model is that you would have what they call n-steps analysis, which are substituted by the number of the rounds that could be used on the general structure, a confusion layer, which is the nonlinear layer achieved by using the addition, which is the the addition box, and then a diffusion layer is used by a mixing layer, by having a mixing layer. So you have the unique aspect of Sparks design is that you have what we call steps and rounds, and it ultimately aims to provide an acceleration level of mixing between linear layers and the confusion layer, which is the addition S-box. This is how it looks like in generality on one iteration of the function and one iteration of the key scheduling. This is what you would see. Because you have a Feistel level structure here, what you get to analyze is we use that to our advantage in order to trace the key similarity. So what we have here is lightweight cipher has a major application and are primarily focused on hardware, such as embedded devices, what we said here. So then what we have focused here on is, can we apply different methods and models of side channel attacks on Sparks? So we started by analyzing timing analysis, power analysis, electromagnetic analysis. So when we're talking about timing analysis, it's about putting the cipher model through an analysis box that would analyze the timing difference between input and output. And if there is a fluctuation on timing difference, then you would be able to deduct information about the execution of the cipher. Of course, basic ciphers, countermeasure techniques, any cipher design would aim to make sure that they counter these timing attacks. We couldn't find any at the moment of the study we've done. For the power analysis, we try to analyze the power consumption of the cipher to deduce the key information. This is what the type of the attack that we have is differential power analysis. For the electromagnetic radiation, we try to check the emission of the electromagnetic of the devices. So again, we have different models when we are talking about the power analysis. We have the simple power analysis that relies on the knowledge implementation of the cipher and the device, and it tries to detect minimal noise and use normally few traces in order to have a successful attack model. And this is the least lower, I would say, the lower bound of any DPA kind of an attack. Differential power analysis, it's a higher level of differential attacks, where the knowledge of the cipher again is sufficient to run this attack. And then you analyze the power consumption dependency of your process data on the power model. And you would, in reality, need more power traces to constitute this attack. When we're talking about a correlation attack, what you're trying to do is build what we call a distinguisher, which is at this moment is called the correlation. And this distinguisher will be a differential power distinguisher or using Pearson correlation coefficient. And then you're trying to resemble the actual power consumption using what we call a Hamming weight or a Hamming distance model. And then it gets easier for you to get accurate results in this sense. So what we went for at the end is the correlation power analysis. So again, first, what did we do to build the power model? We tried to analyze directly the number of bits that are going from transition from 1 to 0 or 0 to 1, which would happen within the registers. And this is what we call directly, this is how you normally build the power consumption. You use an oscilloscope to extract these traces. And normally it would be, reflecting the consumption time of the execution. And then you try to build the Hamming distance between the data, input-output data, and operations of interest. And normally then you get the numbers, you get a specific characteristic between the input and output. And the Pearson correlation it would give you the linear relation between two data sets. So if we have two power traces, for example, of a plain text, and then a Hamming, we can also have a Hamming distance between n number of plain text and encryption results within a specific hypothetical key. Then this Pearson model will help you try to understand first and last round analysis of it. So this is how we build the Pearson coefficient. I'm not going to go through the detail of it, but ultimately what we're trying to do is to analyze the power traces from different plain text encryption with a secret key for each hypothetical key that we are building, because this is what you do again for the Hamming distance model for it, is that to try to build a hypothetical key for each mapping, and then you end up calculating the Hamming distance values between the different plain text with this hypothetical key. And then you calculate the Pearson coefficient between these power traces and the Hamming distance. The highest Pearson coefficient among the different points would be likely the correct key hypothesis, as we have said here. The input, in order to resist against this attack, of course, you can apply what we call a masking algorithm, where you are XORing specific values or mask to the input. So to make it difficult for a random Hamming distance to find these correlations. Then the secret key can be, for example, as a countermeasure, masked using a random result or a random value to resist the first order CPA attack here, what we call correlation power analysis. And our assumption is that this random value generation and masking operation would be performed at different locations and different instances of time. And if that happened, then, for example, TR, which would be the time instance that the random value will be generated at, and TM will be the instance of the masking operation. If you try to apply a differential algorithm in between them, you would have the Hamming distance in between them without the masking. So the first order CPA is performed to derive these power traces. What we need here for the second power trace is, of course, to make it work, more traces and more computations to correlate the power traces and the Hamming distance value. And that's what we've done. For the CPA technique that we have applied, we started to recover the key, starting from the least significant bit to the most significant bit, because we try to count for the carry bits. And this is why we have focused on addition modulo 2 to the power 16. And initially, every carry bit at the low significant bit, at the least significant bit would be 0. And first order CPA technique will be used to extract the least significant byte first. And then we go from there to the other bytes. After extracting the least significant byte, we have to complete 16-bit secret key. We have to complete the 16-bit secret key, which is used in the CPA technique. So first, we have to establish a known value, which is the least significant byte, and then we go to the most significant byte value that ranges from 0 to 2 to the power 8. And then we are assuming that the hypothetical key with the highest piercing coefficient is going to be, again, the correct secret key. This is what we've done here. I mean, using CPA, we focused on 16-bit key, the 16-bit key that's used normally to encrypt this part, and then extracted a 2 to power 9, extracted that 16-bit key with 2 to power 9 key guesses, which is something that's doable within polynomial time. For each 8 bits of the key, we established a Hamming distance, and then we generated the power traces for the second order technique to get the power values, and then the highest piercing correlation coefficient gave us the right, of course, hypothesis. And then the size of this key, which we have developed here, is 2 to 16. It's normally 32 for this branch. If you remember the design, it's actually had 4 branches. It's 32 for it's here. So it has 4 branches, and then you have what we call 16, 16, 16, 16. So we started by attacking this one, and then we deduced the rest, and we moved from here to the full attack. And then again, we use this in an iterative model to retrieve the second part, which is the left part. We retrieve the only unknown part, which is the left part of it, using a CPA model, using a guess of 2 to 9. And this is what helped us at the end of the observation. The observation that helped us perform the attack actually is the fact that the secret key in the first round is maintaining this symmetric similarities. For example, if you looked here, it's actually 0.3 here, this key would be the same as 1.0, so it will not change. And also what we used as well is that, again, 0.3 on this part will be the same here. So we use this preserved, the same, it's not exactly the same. So this one is exactly the same. This one would be similar to having an addition modulo 2 to the 16. So, and then we used this similarity here to substitute for the key here and to deduce the second part. Anyway, going further using this observation, we have been able to perform CPA on round function technique on 4 number of rounds. And this is a published work that we have provided in Africa Crypt. So we try to follow it on, we try to extract key 0 from round 1. Round 2, we try to extract key 1, and using plain text and CPA on round function technique and subkeys 1, 2, 3, 4 of round key 1 and subkey 1 of round 2. We retrieved for each subkey 2 to the power 10 key guesses, and a total number of guesses for the total complexity was 2 to 12. So the hardware specification of our environment was a Cura board where we generated the power traces, and also a Tektronix MS-05204B oscilloscope. The data used on full key recovery are around 65,000 random plain text and encrypted, which is 2 to the power 16, almost to that, using the 128-bit secret key, and the same thing on the other aspect. And then we applied what we call SCA attack on the model. And this is where we got to the point that we need to apply countermeasures in order to improve the design. And these countermeasures are called threshold implementation. It's a scheme that is being proposed by Nikova for provable secure implementation technique using secret sharing. The input to a function will be split into 2 shares, evaluated to produce output shares, and combined again together for the correct output. The threshold implementation, it has specific requirements, 3 actual requirements. The requirement number 1 is to maintain correctness. It means, especially for the splitting and combining of shares, to make sure that they would result in the correct value. Non-completeness, which means each function is independent of the last share, and thus attackers cannot get all the shares. Balance in between these shares, the distribution of input and output should be maintained. And also what we're trying to add beside a threshold implementation, what we called serialized implementation, rather than having serialized implementation of Sparks. It's easier to secure using threshold implementation, which means it makes it difficult for the attacker to make a global deduction. So this is one model for what we have proposed. So we propose that to place the hardware function in a serialized manner, where the rotation is implemented before the XOR, and then rotation is implemented by splitting the registers and stored into 2 halves. And then we implemented on this serialized matter on 64-bit data, and made sure that the linear layer consists of linear function mixes and 32 bits rotation, which is similar to the original design on 16 cycles. And rotation will be done as well on 16 cycles rather than 1 cycle. And the 80 clock cycles would have 48 threshold functions, and the threshold implementation will go from there. So this is how the model is working at the moment. I'm not going to focus on all of the results of the countermeasure. I would recommend, for the sake of time, I would recommend that you revisit the paper. I wanted to make sure that we have enough time to go over our also second contribution, which is towards physical and clonable functions. One of the designs that we worked on in the lab is trying to establish a BUF, which is physical and clonable function, which is a cryptographic primitive that would be used to essentially establish intrinsic randomness for cryptographic applications. Why randomness is important? Because you can use it to generate secret value, and you could use it as well to, as you have seen, to mask the secret value. Traditional BUFs are based on, for example, CMOS functions or ring oscilloscape based CMOS function based on as well ring oscillator. Buffs, arbitrator buffs, static random access memory buffs. They exploit specific and uncontrollable variation models in conventional CMOS fabrication technology. However, they don't provide what we call true randomness nature of the output. They would provide a pseudo-randomness analysis. And current buff designs also face the challenge that there has been an extensive challenge response protocol access time to buffs that poses a limited number of CRPs. And also model building attack. There has been reliability deterioration due to the environment's condition, since they're based on hardware environment. And rarely they will survive an aging perspective. To ensure reliability of cryptographic system, we focus on, for example, how can we make sure that we are designing above that are compliant to low environment power consumption, area consumption, and bit generation speed, high bit generation speed. Also, we focus on this cryptographic strength in terms of the quality for cryptographic randomness. We tested the output to NEST 15 tests, and as well to other reliability and nonlinearity tests. We do resiliency attacks against machine learning, for example. And for us, it's very important to make sure that what we are producing is not a pseudo-random number generators, but actually true random number generators. So we were trying to extract randomness from the physical phenomena of the environment. For example, one of the physical phenomena, which would have specific behavior, such for different nanotechnology devices. I think I have so the memristor that we have built has a specific physical chemistry layer characteristics. We have designed this in our lab, and we changed this CU and CI layers to make sure that we are maintaining a random variations between the voltage alternation that you are seeing here in the graph. And we are also establishing a set and reset cycle that's strong for this device characteristic. Then we have applied a 15 test analysis where the P result has to be, for example, as close as possible to 1. Most of what we have here is a successful attack, is a successful representation of passing the NEST tests. And then what we're trying to do is, as well, we took this buff, we tried to make sure we feed it into a structure of building a cipher. And then we put this cipher in smart meters, and we tested the randomness of the output, and we have achieved as well a true randomness analysis to those buffs. One of the attacks that we are applying is machine learning attacks. We built a framework using logistic regression and other types of attack as well, in order to analyze if it would withstand, if the randomness would withstand these attacks. And what we realized as what we were targeting is to minimize the cost of the cost function using gradient descent algorithm. And we tried to model the attack accuracy for buffs using ideally 50% of pure or equal guesses on the binary output. And we realized that at the end that we kept on maintaining the randomness analysis. So our main contribution is providing a low-cost memristor due to the fact that we only have 3 layers of fabrication structure and low-cost copper electrodes and low power consumption of this memristor that we have designed, which is a hardware security component, a high endurance due to the usage of HFO2 layer. And then we passed a combination of NEST randomness here, and we applied this this randomness, this buff in a block cipher system and in a system of system for the smart meter system to verify the reliability and the randomness of it. The next step for us is to try a photonic structure of this buff in order to accelerate the randomness, the true randomness generation model. And we are striving to push the boundaries of the design and make sure that we demonstrated a full analysis for all of the 2 to 12 key guesses. And this is also a summary of the key recovery that we've done on Sparks. So ultimately, our group is constantly working on analyzing hardware primitives and providing secure hardware primitives in multiple environments. Thank you so much. And if you have any questions, please let me know. I'm sorry because I think I passed my time limit. And I hope that everybody is benefiting from this. I don't know if we have, I don't know if we have time for questions. Feel free to email me. I will send you or WhatsApp me. I'll send you my email on WhatsApp for questions. This is my number. Normally, I place that on the slide for WhatsApp. So I have a question here. It says from Mr. Ananda Mohan, PV. He says, how side channel analysis can be done for post-quantum algorithms, since functions like ADD, round function, etc., are not available? Can machine learning reduce the effort in side channel analysis? Yes, that's what we have checked as well. We built a framework called Dobby and another framework. I'm going to answer the question that's not related to post-quantum first. So can machine learning reduce the effort in side channel analysis? From our perspective, yes. We have reduced massively the efforts that needs, for example, we have went through 65,000 traces in order to produce the Sparks attack. We have implemented a machine learning based framework for the analysis that we used for a different type of attack on AES. And we used it as well for Sparks. And what we have discovered is that because the machine learning algorithms are going through a pre-processing phase to improve the accuracy of the input pool that we have, which is the traces. We ended up using for the attack itself, we ended up using almost half or lower than half of the space with the highest traces, with the traces that has the highest possibility of generating the attack. So yeah, it provided a higher level of accuracy because it reduced the attack space. How can side channel analysis be used for post-quantum? Since the functions like the addition round key are not available, you don't particularly use side channels only for the addition round key. You can use side channels to